Good afternoon, sir. This is Anissa Rahma, and in this presentation, I will discuss the result of our life cycle assessment or LCA analysis comparing to commonly used wall materials in Indonesia, traditional red bricks and AAC or autoclave aerated concrete or lightweight brick. The focus of my analysis is on the construction of type Rumah 36, which is represent one of the most commonly built housing in types in Indonesia, especially within public housing program. This is the table of content. The first one, I will explain about the project overview. After that, introduction to LCA, and then there's impact assessment, and the last one is proposed strategies. Yeah, this is we gonna discuss about the SEC blocks versus red bricks traditional. The first one is project overview. In this slide, I will thoroughly explain the context of the project that served as the foundation of our LCA study. The project we analyze is the construction of type Rumah 36, which is one of the most common housing types used in Indonesian public housing sets. These houses are developed by government program, private development, and independent community effort. The project is stimulated across urban and semi-urban as such as Bekasi, Sleman, and Gresik. These locations were selected to present the first geographic and market characteristic. Bekasi reflects the peri-urban area under heavy urbanization near the capital. Meanwhile, Sleman represent a rapidly growing suburban housing market in Yogyakarta, and Gresik is an example of an industrial and residential growth zone in East Java. These location choice are important because they influence material accessibility and transportation costs and the potential environmental impact. The primary goal of the project is to provide adequate, affordable, and most importantly, environmentally friendly housing. As the world strives to reduce carbon emission and achieve sustainable development, it is essential not only to consider technical and cost aspect, but also to evaluate environmental impact throughout the building life cycle. Therefore, in the study, I will be focused on the wall component and compare two material between red bricks and AAC lightweight brick. Why walls? Because in terms of volumes, walls account for approximately 20 to 25% of the total material used in a house. This means that the decision regarding wall material selection has a significant influence on total carbon emission, energy consumption, and material and labor costs. To provide some context, red bricks is a traditional material still widely used in Indonesia. It's often produced through manual and small scale process and tends to have high energy efficiency. In contrast, AAC is a modern alternative that is increasingly popular due to its lightweight nature, thermal insulation properties, and installation efficiency. This slide lies the foundation for our LCA study. All environmental, technical, and economic consideration in this presentation stem from the context of construction type of Rumah 36 as described here. And then the next slide, there is Introduction to Life Cycle Assessment, or LCA. This slide serves as a foundation of my entire analysis. Before diving into the data and technical compression, we first need to understand what life cycle assessment, or LCA, actually is. By definition, life cycle assessment is a methodological approach used to evaluate and quantify the environmental impact of a product, process, or activity from the beginning to the end of its life cycle. This is often referred to as a cradle to grave approach, which means that every stage is considered from raw material extraction to end of life disposal. There are five main stages in a material life cycle that are assessed in LCA. The first is raw material extraction. The second is production process. The third is transportation. The fourth is uses stage. The last one is end of life treatment or wasting processing. For the raw material extraction, these include all activities relate to harvesting or mining of raw materials. For instance, red bricks require clay to be extracted from natural sources, while AAC involves materials such as like silica sand and cement. This stage often contributed significantly to environmental degradation, energy use, and greenhouse gas emission. And then the second one is production process. Once raw materials are obtained, they are processed into finished product. For the red bricks, these include firing and kilns, whereas AAC brick are cursed using autoclaving and this step is critical as it typically account for a large portion of a total energy consumption and carbon emission. And then the third is transportation. The manufactured material must be delivered to construction site. The distance traveled, type or vehicle use, and overall logistic efficiency and all influence the carbon footprint. For the example, although AAC is lighter and the factory is located from for the project site, transportation emission can still be significant. And then the fourth is usage stage. This is the period during which the material function as a part of the building. Not all material have significant impact at this stage, but factors such as thermal insulation performance, weather resistance, and contribution to building energy efficiency are important. For instance, ASC bricks over better thermal insulation than red bricks, potentially reducing the need for cooling energy. The last one is end of life treatment or process processing. Once the building reaches at the end of its use, the material become waste. The stage assesses whether the material can be recycled, reused, or need to be landfill. Red brick are generally harder to recycle, whereas AAC can be crushed and reused as lightweight aggregate in secondary application. By understanding each of that stage, we gain a comprehensive view of how a material affects the environment, not just during use, but throughout its entire lifespan. This is what makes LCA a critical and relevant approach for making sustainable decision and for making sustainable decision in the construction industry. Okay, next slide. I have life cycle stage. This slide systematically outline the life cycle stage of the wall materials we are studying, red bricks and AAC lightweight bricks. The life cycle assessment approach require us to examine the environmental performance material from start to finish. So let's break it down step by step. The first is raw material extraction. There's a brick and made from clay that is extracted directly from the earth surface, often from agricultural lands or yard. This led to environmental issues such as land degradation, loss of fertile land, and change in the ecological landscape. The extraction of clay can also have social impact as it competes with agricultural land. So next one is AAC lightweight bridge. On the other hand, use natural byproducts such as fly ash from coal-fired power plants. This help reduce industrial waste. In addition, AAC requires cement and silica sand, which still need to be mined, but in the different proportion compared to the clay use of red bricks. The second one is production process. Red bricks is typically produced through traditional methods. The process is very simple. Clay is manually shaped, dried, and then fired in open kiln using firewood or coal. This results in significant greenhouse gas emission and local air pollution from dust and smoke particles. In contrast, AAC is produced using modern method. The materials are homogeneously mixed, then molded and cured in an autoclave, which is a high pressure and high temperature reactor. Although this process consumes a considerable amount of energy, its production efficiency is higher, and emission can be more effectively controlled in closed industrial system. The next one is transportation. Red brick is usually produced locally and near to the project site. The distribution distance in short, typically less than 20 kilometers, resulting in relatively low transportation emission. On the other hand, AAC often needs to be transferred from large factories to maybe locate from 50 to 200 kilometers away from the construction site. Well, the material is lighter, allowing for the transport of larger volume per trip. The longer transport distance, they'll contribute to a higher carbon footprint for transportation. The next part is uses. Red brick has several disadvantages during use. Due to density and weight, installation is slower and require more labor. Additionally, it has a high water absorption high water absorption rate, making the building prone to moisture and requiring additional coating. Then, from a thermal efficiency standpoint, red bricks is less effective at insulating heats. Meanwhile, AAC is known for its much better thermal and acoustic insulation. It is much lighter, about 1/3 the weight for the red brick. So it speed up construction, reduce the structural load, and lower fixed vertical logistic costs on site. Is end of life. When a building with red bricks is demolished, the material typically becomes solid waste due to irregularness and impurities from red brick is difficult to recycle. Many of that brick end up in landfills or are buried again in the soil. But conversely, AAC can be crushed and reused as land waste, road-based layer, or in non-structural concrete mixers. This makes AAC is a better option in terms of the circular economy. Through the symmetric compression, we can begin to see the bigger picture. Material selection is not just about price and availability, but also about its environmental impact from start to finish. This from the basis for the subsequent LCA analysis. Okay, next slide is goal and scope definition. In this slide, I will dive into the goal and scope definition of the life cycle assessment or LCA analysis we are conducting. The LCA process aims to provide a comprehensive understanding of the environmental impact of two types of material used in the walls of type 36, red brick and AAC brick. Let's break down the key elements of this definition one by one. Is goal of the LCA. The primary goal of the LCA is this study is to compare the environmental impact caused by two types of building material, red bricks and AAC brick. We focus on wall with an area of 1 square meter, where we will measure various environmental parameters throughout the material life cycle, such as greenhouse gas emission, energy consumption, water uses, and loss of generation. This comparison is crucial because both materials have very different characteristics, especially in terms of production, process, and material use. For this goal, we aim to identify which material is more environmentally friendly in terms of natural resource use and emission generate. We also aim to provide recommendation for developers of type Rumah 36 to choose more sustainable material in their building construction and help consumer make better choice in terms of sustainability. The second one is functional unit. The functional unit we have chosen for this comparison is 1 square meter of wall. Why choose this unit? Because walls are a key element in the building that affect thermal, structural, and aesthetic performance. In the context of type Rumah 36, walls are one of the most used components. We also ensure that the wall's thickness and thermal performance are equivalent between red brick and AAC, assuming that both serve the same function in terms of head insulation and durability. This allows for a fairer comparison between the two materials. Some bonders. For this analysis, we use cradle to grave system bonders, which encompass the entire life cycle of the material being analyzed. The term cradle to grave refers to an approach that includes all stage from raw material extraction or cradle, meaning the natural resource used to produce material, to the end of the life cycle, which is demolition and potential recycling or scrap. This boundary ensure that we are not only looking at the impacts of material production, but also long-term use and the final management of the material use, such as recycling or waste disposal. In this case, we will make sure that the environmental impact at every stage of the process, including raw material extraction, brick production, transportation to the construction site, installation, building maintenance during the service life, and finally demolition and end of life material processing. The last one is assumption. To simplify the analysis, we have made several basic assumptions that apply throughout this study. Construction and maintenance will follow typical standard for type Rumah 36, including material maintenance, condition, and building durability during everyday use. We assume that there will be no significant maintenance or renovation during the service life of the walls. We also assume that the both type of material will be produced with current technology and in accordance with applicable industry standards. For example, for red bricks, we assume that the firing process will be conducted efficiently according to current industrial practice. For the SSC1, we assume that use of available fabrication technology considering the energy and raw material used in production. By clearly establishing this goal and scope, we can focus on comparing the two materials directly and ensure that the analysis is fair and representative of real-world conditions. And next slide, I have life cycle inventory or LCI. In this slide, I will discuss the life cycle inventory or LCI, which is the stage that maps inputs and output associated with the life cycle of the two materials we are comparing, which is red bricks and AAC bricks. LCI is important because it provides a clear picture of raw material production process, energy use, transportation, and the waste generates. Let's break down. The first is raw materials. The red bricks, the primary material for making red bricks are clay and water. And AAC brick for the raw material used are more varied and complex, like fly ash, a byproduct from coal. Combustion is the main material used, which help reduce industrial waste. Additionally, cement, gypsum, and aluminum are used to provide structural strength and durability to the bricks. The second is production process. After raw material are obtained, this material undergo a very different production process. For the red bricks, the production process of red bricks involves firing at high temperature around 800 sampai 1000 derajat Celcius, which requires a large amount of energy. This firing process use fuels like a coal or wood, which inevitably generates greenhouse gas emission and other pollutants, will significantly increasing energy consumption. The long firing process, whilst the long firing process and high temperature also produce harmful particle emission that can affect the surrounding environment. For the AAC brick, the production is more energy efficient as it uses autoclaving at a temperature of around 180 derajat Celsius and a pressure of 12 bars. This process is more environmentally friendly compared to firing because it uses electricity and steam that the energy source. The more energy efficient, also plug-in still requires significantly energy, the not so much of firing red bricks. And then the next part is energy. The red bricks, as mentioned, the production of red brick requires high energy consumption due to the firing process and high temperature. This process heavily relies on fossil fuels such as coal or wood, which result in significant carbon emission. AAC bricks. On the other hand, the production of AAC bricks require moderate energy consumption. The autoclaving process relies on electricity for heating and steam to achieve the necessary pressure. While not relying on direct combustion energy use, is still considerable, though lower than for red brick production. The fourth is transportation. Typically red bricks are produced locally, and transportation distance are relatively short. The carbon footprint from transportation as long distance shipping is not required. For the AAC brick, are often produced in large factories that are more centralized, which might result in longer transportation distance between cities for distribution. This transportation requires more energy, increasing the emission associated with it. And then the fifth is production waste. The firing process, the red brick produces ash and particular emission, which are one form of waste that can pollute the air and soil and so on. This ash is often poorly managed, posing challenge in reducing the environmental impact of the red brick production. Meanwhile, AC brick include wastewater and slurry, which are residues from the mixing of raw material. If not properly managed, this waste can pollute water source, although is often recyclable or further processed. The next part is impact assessment. This is the slide about carbon emission. In this slide, I will discuss the carbon dioxide or CO2 emission generated by the two materials being compared, namely red bricks and AAC brick. CO2 emission are key parameter commonly used to assess the environmental impact of a material product. Carbon dioxide is the primary greenhouse gas that contributes the global climate change. Therefore, measuring and comparing the carbon dioxide emission generated by the two material is crucial in determining which is more environmentally friendly. CO2 emission from red bricks. CO2 emission or carbon dioxide emission per meter cubic of red brick range from 250 until 300 kilogram carbon dioxide. This figure refers to the emission generated during the production of red bricks, primarily from the high emission generated during the production of red bricks, primarily from the high temperature firing process that requires significant energy and fossil fuel use. And carbon dioxide emission per meter persegi of red brick are around 75 sampai 90 kg carbon dioxide. These figures are based on the thickness of the red brick used is the standard walls, and the is based on the thickness for the red brick used in standard walls, and the carbon dioxide emission generated per unit volume of the bricks. Okay, next part is CO2 emission from AAC brick. For carbon dioxide emission per meter cubic of AAC brick are lower, ranging from 170 sampai 200 kg CO2. The production process of AAC brick is more energy efficiency, considering that is a main raw materials is applied as, which is in industrial waste that help reduce the carbon footprints. For per meter persegi AAC brick wall are around 50 sampai 65 kilo. This is lower than red bricks. The more energy efficiency autoclaving process, which use less fossil fuel compared to the flaring of the red bricks. Okay, we have calculation the minimum for red bricks carbon emission is 25 kilo karbon dioksida per meter persegi, dan maksimumnya adalah 300 kg per meter persegi ya. 30 kg per meter persegi malah. In this calculation, we can see that CO2 emission from red bricks is higher than AAC brick. It's just only about 17 kg CO2 per meter persegi, and maksimumnya adalah 20 kg CO2 per meter persegi. Insights into the carbon emission related to these two material, we refer to several sources like Green Gems 2022 in the article title are ACC block fairly green, which discuss the environmental impact of various building materials, including the comparison between red bricks and AAC. And then we have other environmental impact. In this slide, I will explore several other environmental impacts that need to be considered in addition to carbon emission. This impact include aspects such as water consumption, air pollution, construction waste, and electricity use. Well, carbon dioxide emission are one of the primary indicators in assessing environmental impact. These other factors are also critical comprehensive assessment. Let's discuss this aspect in detail. The first is water consumption. Water consumption for red bricks, the production of the red bricks doesn't really heavily on water consumption, as the primary material used is clay, which requires minimal water during mixing and shaping. Water is mainly used for forming the mixtures and moistening the clay before firing. And then for the AAC, the production requires more water, especially during the curing and autoclaving process. During curing, the AAC blocks AC bricks must be treated with a specific level of humidity to achieve the desired strength. Furthermore, the autoclaving process requires a substantial amount of water in the form of the stem to create the pressure and temperature needed for the process. However, the water used in AAC production is more controlled and can be recycled during various stage of production. The second one is air pollution. One of major environmental impact of the red brick production is air pollution, particularly from the burning of fossil fuels like coal and firewood at very high temperature, like 800 sampai 1000 derajat Celsius. This burning process produces particulate matter, which can pollute the air and negatively affecting air quality around the brick manufacturing facility. This particle also contribute to greenhouse gas emission and local air pollution, which can be harmful to human health. And then we have lightweight bricks. The AC block production process while relying on electricity and steam. It's cleaner in terms of air pollution. It doesn't involve burning fossil fuels. Therefore, AC production generates fewer particular and harmful gas that pollute the air. Additionally, by using processed materials such as fly ash, AAC also reduces its negative impact on air pollution. The next part is construction waste. For the construction waste, red bricks tend to be more fragile and break easily during construction. This means that during the construction process, most waste is generated, both from broken bricks and from discarded pieces. Therefore, the construction waste produced by red brick use can be higher compared to AAC bricks, which are more resistant to physical damage. And for AAC are charger and lighter, minimizing damage during transportation and installation. As a result, the use of AAC bricks can reduce the amount of construction waste generated because they less likely to break and can be installed tightly, reducing leftovers and discard pieces. Part is electricity consumption. For the red bricks, the red brick doesn't really heavily on electricity consumption, as most of the energy comes from the burning of fuels. While some factories might use electricity for automatization or transportation process, overall electricity use is lower compared to AAC blocks. For AAC, require a significant amount of electricity, especially for the autoclaving and curing process. AAC factories need a stable and sufficient electricity supply to maintain the temperature and pressure required for block production. However, despite the relatively high electricity used during production, building using AAC blocks tend to be more energy efficient in the long run due to their excellent thermal insulation properties, reducing the need for heating and cooling. This reference for Green Gems 2022 and EdTech 2023. Okay, next slide. I have some energy consumption. Energy consumption include three main stages: production, operational, and distribution. Stage have a significant impacts on the energy footprint of this material, which is a true contributor of the overall environmental impact. Yeah. The first one is we talking about production. Red bricks requires high energy, primarily due to use of traditional kiln or forging, yeah. And then this process consumes a large amount of fossil fuels, such as coal or firewood, which not only requires significant energy but also produce substantial greenhouse gas emission. Therefore, energy consumption in the production of the red bricks high compared to other materials. For AAC, our product more automated cement, fly ash, and aluminum before being processed in a pressurized and high temperature chamber. Also, this process requires energy and in the form of electricity and steam. The energy consumption during the production of AAC bricks is moderate compared to red bricks due to the more controlled autoclaving process, which use less energy than bricks. Brick fairing, sorry. Therefore, while still energy intensive, the production of AAC bricks is more energy efficient rather than red bricks. Next part is operational. Red bricks, one of the major drawbacks is the poor thermal insulation. Walls made from red brick don't have good insulation properties, meaning buildings constructed with this material are more susceptible to external temperature of vacation. And then to maintain indoor comfort, the use of air conditioning becomes essential. This leads to high electricity consumption for air conditioning operation, contributing to high energy consumption during the building's operational path. The way AAC bricks have excellent thermal insulation due to their porous structure, which help maintain a stable indoor temperature. With better insulation, the need for air conditioning is reduced, leading to more energy efficient climate control. In the long term, using AAC blocks can reduce energy consumption for both cooling and heating, making them more environmentally friendly option in terms of building energy consumption. Next part is distribution. In terms of distribution, red bricks are generally produced and distributed over shorter distance, and AEC blocks is maybe some the project location the product far from the product location as factory stand to look at is more centralized area to meet large scale demand. And then the longer distribution distance mean higher energy consumption for transportation, yeah. And then next part I have quality and performance. For this slide, compressive strength, red bricks, the compressive strength range from 5 until 10 MPa. This strength is adequate for most residential building application, but it's not as high as some modern materials. While sufficient, red bricks have a limitation in strength compared to more modern material like concrete or AAC block. For AAC block, a lower compressive strength around 3 until 5 MPa. This makes AAC block more suitable for use in non-structural walls of part of the construction that don't bear significant loads. However, this lower compressive strength is still adequate. I mean, for residential building like type tipe 36 rumah tipe 36 where the load is not too heavy. The next is weight. Red bricks are heavier than AAC bricks. These additional weights contribute to greater structural strength, but also increases the total load of the building structure. This affects transportation costs and requires more labor for installation. The next is AAC bricks. The key of advantage of AAC bricks is that they are 50 until 60% lighter than red bricks. This makes transportation and installation easier and reduce the structural load on the building. The next is installation. Red bricks are installed traditionally using mortar and binder. The installation process takes more time because each bricks must be placed individually with less precision. Additionally, the heavier weight of the bricks requires more labor to move and install them. Meanwhile, AC bricks is much faster, cleaner, and more precise. Due to their larger size and lighter weight, the installation process is quicker than less mortar. Using AAC brick, the installation of AAC brick is much faster, cleaner, and more precise due to their larger size and lighter weight. The installation process is quicker with less mortar, resulting in a neater finish. AAC blocks are often used with cement-based devices which are more efficient in installation compared to mortar used with red bricks. The fourth is thermal insulation. Thermal insulation. Red bricks have low thermal insulation properties. That mean the walls made from red bricks tend to heat up quickly in the summer and cool down quickly in the winter. Well, AAC blocks have excellent thermal insulation. The porous structure of AAC bricks allow them to maintain stable indoor temperature both in summer or winter. The next is sound insulation. Red bricks offer moderate sound insulation. While they can reduce some outside noise, the walls made from the red brick cannot completely block noise from external environment or from other room within the building. For the AAC bricks, their porous structure are more consistent thickness, offer better sound insulation than red bricks. Maybe I will add about fire resistance. For the red bricks, have a good fire resistance due to their normal clay composition, which withstand high temperature. However, their fire resistance is limited to a certain temperature range and may degrade if exposed to extreme heat for extended period. But for AAC blocks, AAC bricks, I mean, also have good fire resistance too, even better than red bricks, made from material like cement and fly ash. That the resistance to high temperature. AAC bricks can withstand fire for a longer period, providing additional protection to the building structure. This is reference for vessel and 2024 and then the next slide. The next slide I have cost compression and construction efficiency. This slide is crucial for understanding the connection between economic aspect and construction efficiency in relation to the principle of life cycle assessment, or LCA. In LCA, cost is not only viewed from the perspective of material per cast price, but also includes installation time, labor requirement, and the structural efficiency per unit volume of the material, which ultimately contribute to overall environmental footprint throughout the building life cycle. Per meter persegi per meter kubik. Red bricks have a relatively lower initial price, around 700.000 sampai 850.000 per meter kubik. However, its economic value is mostly abandoned at the point of initial purchase. On the other hand, autoclave or AAC is priced higher than red bricks, about 900.000 sampai 1.100.000 per meter kubik. But this needs to be analyzed in the context of functional value per material volume. The important note is, while AEC is more expensive per meter cubic, the amount of wall area that can be built per meter cubic is greater, meaning the cost per meter persegi of effective wall area can be cheaper. This is an important point from an LCA perspective. We evaluate the impact and value per functional unit, not just per material unit. Labor costs, the red bricks generally require more time for installation during their smaller size, and traditional techniques leads to inefficient labor costs in terms time and number of works. Conversely, AAC being larger, lighter, and more precise, allow the faster and more efficient installation, requiring fewer workers and less time. The important in the context of LCA is the cost and energy used for file activities are part of the construction path in LCA. The more efficient in the construction process in time and labor, the lower the CO2 emission, energy consumption, and potential construction waste. Next part is installation time. Untuk rumah tipe 36 house requires approximately 7 till 10 days to install red bricks wall, while with AAC it can be complete in just 3 until 5 days. This is not just about project timing, but also involve the use of equipment, daily energy consumption, and logistics, all of which contribute to the overall environmental footprint. LCA explanation for the reference is from Fashit and 2024 about life cycle assessment of traditional clay bricks and so on. While AAC might appear more expensive in initial cost when viewed holistically through the LCA approach, which consider time, efficiency, labor, and effective volume. AAC actually offers superior economic and environmental benefit. They highlight the importance of evaluating the project is not just by the material forecast cost, but by the entire life cycle. And then next slide, I have about proposed strategies. This slide serves as a conclusion and practical step from the LCA finding present in the previous slide. For the four strategies outlined here are designed to optimize the use of building material while maintaining energy efficiency, cost effectiveness, and environmental sustainability, particularly in Rumah 36 house project in dense and massive in Indonesia. The first one is hybrid uses, a combination of red brick and AACC. AAC, I mean. This strategy combines the strengths of both materials based on their functional. Exterior walls are used red brick because their higher compressive strength capable for withstanding structural load and extreme weather exposure. But interior walls or partition use AAC because it's lightweight, quick to install, has excellent thermal and acoustic insulation. The hybrid system reduces overall material and energy consumption without compromising performance. This is relevant in both the construction and use paths of LCA, as it reduces work time, construction emission, and save on cooling energy or operational emission. This reference for Anwar M. et al. 20 to 23 cost environmental optimization in hybrid wall construction. The next part is incentive for a local AAC production. One of the weakness of AAC in LCA is transportation emission due to the long distance that AAC break are shaped sometimes between cities or even province. By intensifying the establishment for local AAC production plants, transportation distance can be drastically reduced. This also reduces fuel consumption, carbon dioxide emission from transportation, and speed up supply the project. This strategy optimizes the transportation paths within the LCA boundary, which can be quite significant or large scale project. Moving the projection closer than the project site is known as a geolocation optimization in LCA literature. And then next, we have training for mason and contractor. AAC requires different installation techniques compared to traditional red bricks, including cutting, advanced use, and light drilling. Without proper training, the risk of installation failure increases, leading to material waste, rework, and overconsumption energy. Training can be provided through practical LCA models of for mason, so they understand the environmental consequence of waste. Construction waste and labor efficiency are part of the construction and waste management path in LCA framework. Training can reduce impact in categories such as global warming potential, or cumulative energy demand, or petrochemical or ozone creating potential. And then the last is evaluate project emission hostly collidro LCA. The government can mandate LCA as a requirement for design verification and environmental reporting. This allows developer to adjust material choice and work method based on environmental impact data rather than just cost. Policy implication and standardizing LCA will drive decarbonization in the housing sector, supporting Indonesian net zero emission target by 2060. The strategies show that life cycle assessment is not just a technical analysis tool, but also a guide for policy and practical design. By combining structural efficiency, logical optimization, workforce training, and data-driven policy, we can develop Rumah 36 project that are not only affordable but also sustainable from start to the finish. The next part is we have the conclusion. Red brick is suitable for small-scale project using locally available material, but has a higher environmental impact due to the framing process and resulting waste. In contrast, AAC offers better thermal insulation, is significantly lighter, and allow for faster installation. Although AAC has for a lower carbon footprint, its benefit depend on efficient production and transport management. AAC is recommended for a large-scale housing project focused on energy and time efficiency, while red bricks remain an option of smaller project or where AC access is limited. Incorporating LCA is essential for selecting sustainable building material. And then this is to prepare the life cycle assessment analysis. I didn't rely on a single source, but it's a great various credible reference from national and international standard academic journals and lab simulation tools. For national standard regulation, I have SNI nomor 03.303.491989 and so on. And for international LCA standard, I have ISO. We refer to ISO standard from basis of the LCA methodology or scientific source like journal from Green James and AirTag were also used to examine industry term about ACC material, including the limitation. All right, I think that's all for me to present today. That's all, sir. Thank you for attention and good night. Assalamualaikum.